Welcome to the week 4 in which we will discuss about device and input output management in operating system. Input output devices are the only way users and the external systems interact with the system. So without the input output, your computer is just like a processor and memory. So input output operations often become performance bottlenecks because device speeds vary dramatically. For example, a keyboard processes keystrokes in milliseconds while an SSD can transfer gigabytes per second. So operating system must hide device diversity and provide a consistent interface, we'll say. For instance, whether saving it to a USB or SSD or to a cloud drive. Applications just call the write method. So operating system handles that complexity. So the key challenges are using the input output devices are device diversity. Like we are having different types of devices. We have printers, disk, GPUs, CPUs, keyboards, etc. Different speeds. Every device has a different speed. And shared access, like multiple applications may want to use the same printer or hard disk simultaneously. So this is the structure of input output system, which is split it into the hardware and software layers. So input output hardware consists of your ports, buses, device controllers, and device themselves. Okay, device independent operating system softwares provides uniform handling of all the devices, like we see buffering, caching, error handling, and so on. Then we come up with the device drivers, which are the specialized softwares. So specialized softwares that can translate your operating system commands into the specific, um, which can translate your in sorry this one, yeah. Specialized software modules that translates your operating system level commands into the device specific instructions. Okay, then we have some user specific libraries. So user specific libraries, which are basically used to convert higher level APIs like printf, which we use in C++ or C, that simplify your input output, simplifies input output for programmers. Just you as an analogy, I can say, just think like a supply chain. The application is the customer, device drivers are the warehouse workers, and the operating system is the manager, ensuring orders are handled consistently. Then input output hardware, ports, buses, and controllers. So what is a port? A port is a connection point. It is a physical connection point, like we have in our laptops, USB ports, HDMI ports. Buses, the communication highway that connects CPU memory and device drivers, for example, and different devices, right? Then like we have SCSI, USB, number of buses we have. Then we have the controller, which are also known as adapter. These work as a translator between the CPU and the device. So it manages the device specific task, like moving a disk head or converting data signals. And the controllers contain registers that the CPU reads and writes for controlling and the status, right? So whenever we need to communicate with the controllers, that is, we require the input output registers. So devices with the spatial registers are used. Devices have the spatial registers for communication, like we have data in register, data out register. So data in register holds data read from device, and data out register holds data to send to the device. We have a status register which maintains that which device, the status of the device, like it is ready, busy, error, like that. And we have control registers in which let CPU configure device modes or issue commands, right? For example, when you are typing on a keyboard, the key press is stored in the data in register until the CPU retrieves it. So these are the data in register, data out register, status register, and control registers. Then methods for input output port communication. We have memory mapped input output and we have port mapped input output, which are also called as isolated input output. So in memory mapped input output, device registers are mapped into the system's address space. The CPU can use normal load and store instructions to access them. Whereas in port mapped input output, it uses a separate address space with special instructions like in and out. So modern operating systems often uses the memory mapped input output because it simplifies your programming. So you can see here one is the memory control line and one is the input output control line. One we have programmed input output, which is also called as polling. So in this one, CPU repeatedly checks the device's status register until it is ready. For example, a printer may take time before it can accept the next character and CPU and it waits the CPU cycles in waiting. So this is called as busy waiting. So it is inefficient, especially if the device is slow. This is the diagram basically that how the process goes on for the input output. So to avoid the wasting time of CPU, the busy waiting time, the efficient alternative is the interrupts. Instead of polling, devices notify the CPU with an interrupt when they are ready. So CPU gives a command, it does another task, device signals via the interrupt. So CPU temporarily pauses the work, runs the interrupt service routines, which are called as ISR, and then it resumes. You can think of like it that instead of constantly checking the oven while cooking, that is the polling, the oven timer interrupts you when the food is ready. So this is the chart that how the steps how it takes place. Interrupt mechanism. For handling the mechanism, we maintain a interrupt vector table. It is a lookup table mapping each interrupt type to the correct ISR. So the ISR responsibilities are CPU, saving the CPU state, identifying the cause that which device triggered it, then handle the event, that is copying the data from the device buffer and so on, and restore CPU state and return. So basically it efficiently depends on minimizing the ISR execution time. So this is the structure of interrupt vector table, that how it looks. The interrupt number provides an index into the table and the function, it gives you the function for each interrupt handler. You can say this in the table also that main program has some instructions. If an interrupt generates, it checks into the interrupt vector table. And then from the interrupt vector table, we get the ISR entry. Accordingly, then we can execute it. Then we use the DMA, which is direct memory access. Even with interrupts, transferring large data blocks is CPU intensive because each byte still involves CPU. So to avoid it, we use the DMA controller. These are the specialized hardware that directly moves data between device and memory. CPU only sets up the transfer, that is the source, destination and size, and resumes work. DMA interrupts the CPU only once when the whole transfer is done. So it is the responsibility of DMA, that is your direct memory access controller, to move the data between memory and the disk, between source and destination as defined by the CPU. So how DMA works? First of all, CPU configures the DMA controller with source, destination and byte count, which is the size, that how many bytes needs to be transferred. Then DMA controller takes over and manages the transfer. CPU continues with the task. Once done, DMA controller interrupts CPU to signal the completion. It is something like that copying a disk block to memory without copying CPU without using CPU cycles for each byte. So this is the chart that how basically it works. DMA is the we use the DMA, which is deals directly with all the input output devices to transfer the data between devices and the memory. It takes instructions from the processor. If you see in this one, device driver is told to transfer drive 2 data to buffer at address this. This is the instruction generated by CPU. Then number 2 is device driver tells device controller to transfer C bytes to buffer at address X. So it will perform the operation. Then at number 3, drive controller initiates DMA transfer. Then DMA controller transfer bytes to buffer X, increasing memory addresses and decreasing C until C is 0. So because you need to transfer each byte. And when C is 0, that means the transfer is done. The DMA interrupts CPU to signal transfer completion. So this is basically how it works, their DMA works. DMA transfer modes, we have two transfer modes. One is the burst mode and one is the cycle stealing mode. In case of burst mode, DMA locks bus until entire block is transferred. It is very fast method, but it starves the CPU because meanwhile CPU cannot do anything. The reason the buses are locked. On the other hand, cycle stealing method, in which DMA transfers one word at a time, interleaving with CPU operations, it is slower but fairer. So, trade-off between performance and the system responsiveness. Application input-output interface. Then, operating system provides a uniform input-output interface for applications. Device drivers act as translators. Application makes a generic request like read and write. Drivers convert it into the device-specific commands. For example, saving a file looks identical whether on hard disk drive or SSD or USB. Because the differences are handled by the driver. You save any of the file, it is identical on each device, right? So because all the mechanisms are handled by the driver. So and these are the software and hardware. The hardware deals directly with their device controllers or which device controllers on the other hand deals with the device drivers and which deals with the kernel input output system, and then we have the kernel. So the same thing, like each input output device, whether it is monitor, keyboard, hard disk, they have their own interface to deal with address bus, data bus, control bus. Now, disk management. Disk, so disk uses platters coated with magnetic material. Disk we use to store our data. These are the permanent storage. So data is stored in tracks, which is the some concrete circles divided into sectors. A cylinder is a same track position across all the platters. So this structure impacts how data is accessed and how scheduling is optimized. If you see in this diagram, mhm, okay, if you see in this diagram, you can see there are multiple platters. Each platter is in the middle, there is a spindle on which it rotates. Then each platter is divided into some tracks. This is the circular circles are called as tracks. And each track is divided into the sectors. So a cylinder is from all the platters. If we use the same track position across all the platters, that is called as a cylinder. So older methods to address the data, we uses the CHS, that was the cylinder head and sector. That is, we need to provide the cylinder number, head number and sector number, that which data we need to access, which data we need to read. Nowadays, we uses the LBA method, which is called as logical block addressing. It is a linear addressing mechanism used by operating system. So in this one, disk controllers translates your LBA, that is logical block addressing, to the physical cylinder head and sector. How we can check that what my disk performance should be? It is the matrices which we use. Is the access time, which is the addition of seek time plus rotational latency plus transfer time. Seek time is the moving disk head to the correct cylinder. Rotational latency is waiting for sector to rotate under the head. Then transfer time is reading, writing the actual data. So these parameters basically directly affect your disk speed. If we calculate the access time, for example, a disk rotates at the speed of 15,000 RPM, that is revolutions per minute disk. Okay, 2 millisecond is the disk time, 512 byte sector, and 100 MB per second transfer speed. So we need to calculate the average rotational latency, which will be zero point 0.5 times 60 over 15,000 times 1000. So approximately 2 milliseconds. The transfer time will be 512 divided by 100 megabytes per second, which comes out to be approximately 0.005 milliseconds. And the total time will be 4.005 milliseconds. So seek plus latency time we use. Then we come towards the disk scheduling. When the operating system receives multiple requests, right? So order of servicing request greatly affects the performance. Like we need to minimize the head movement and waiting time. And the bandwidth, that is the total data per time, and response time improves with smarter scheduling. So which data should be, if we are having the multiple requests to read data from the disk, which data should be read first and which data should be read last? We need to perform for that disk scheduling algorithms. We have multiple disk algorithms. Like first one is FCFS, that is first come first serve. It is the simplest algorithm, simplest and fair algorithm, but it is poor for random workloads. For example, if you are having a queue of disk head requests 98, 183, 37, 122, 14, 124, 65 and 67, and currently head starts at 53. So it starts with 53, then the request is for 98. So from 53, your head will go towards the 98. Then from 98, it will go towards the 183. Then from 183, it will go towards the 37, then 122, then 14, and so on. So if we see the total head movement, it will be 98 minus 53, because my currently head position is at 53 and it goes towards the 98. So 98 minus 53 plus 183 minus 98 plus 30, 183 minus 37. Look, we always take the absolute value because we just need to calculate number of head movements. So if you calculate all of the head movement, it comes out 640 cylinders. Then next algorithm which we use is SSTF, which stands for shortest seek time first. It picks the nearest request first. So it is its average time is good, but it may have the possibility of starvation. Like the cylinders who are far away, and always you are getting the request for the nearby locations. So the starvation will be there for the blocks which are far away. So again, if we are having the same request, the same string, so from 53, the nearest one is 65. So it will go to the 65, then it will go to the 67, then 98, then 122, then 124, and then 183. Then it will go towards the 37 and then 14. So total head movement becomes very low in this one. You can calculate it. Then the next algorithm is the scan algorithm, which is also known as elevator algorithm. It moves back and forth serving along the way. So it is one of the fairer algorithm. The disk arm moves in the one direction. It's something like the elevator, like it first goes in upward direction, serving all the floors, then it goes towards the downward direction, again serving all the floors, then upward, then downward. So in the same way, scan algorithm, first it goes towards one direction, serving all the requests till the end of the disk, and then it goes in the reverse direction, again serving all the requests in that direction. So it is the fair algorithm, there is no chance of starvation. So if you say in this example, let's say my queue is again the same one. So from 53, first it is going towards the left direction, whichever requests are there in the middle. Like from 53, it will go to the 37, then 14, then 0, because it will go towards the end of the disk. Then from 0, it will go to the 67, 65, then 67, then 122, 124, then 183, and so on. So first it goes in one direction, then it goes in the other direction. Then we have circular scan. It treats all your cylinders in a cylindrical way basically. It only moves one way, then jumps back. So the waiting time is uniform. Oops. Yes. So it, first of all, it goes in one direction. If you see, then it jumps back towards the beginning of the list. It is not handling any request, and then it again goes towards the um, request, serving the request. So it always move in one direction, serving the request, and then it goes back. It goes one direction, then serving all the requests, then it comes at the beginning of the disk, and then it again start moving, serving the request. Then we have look and circular look. Look and circular look are similar to scan and circular scan, but it avoids it stops at last request rather than going towards the beginning of the disk or ending towards the disk. If you see in these previous examples, your head, the last request served was 14, but still it goes towards the 0. So from 0 to 14 is the extra head movement. So in look and circular look, we goes only towards up to 14. Then since this is the last request, there is no more request, then it will start going in the next direction. So it avoids, there is less wasted movement. The wasted movement which we are doing in scan and circular scan, those will not happen here. So these are more efficient as they don't waste time traveling at the absolute ends of the disk. So if the request queue is something like this and the head starting position is 53, then you can calculate your total number of head movements by using all of these algorithms. No, if we need to choose which disk algorithm we should use, choice actually depends upon the workload. SSTF is one of the most natural algorithm and it is common for general operating system. Scan and circular scan are better for heavy loads. Modern SSDs actually do not need such kind of algorithms because there are no moving parts. Okay, so these algorithms are not relevant to the now modern day systems. The next concept comes of buffering. Buffer is a memory which is used to hold the data during the transfer. The purpose of buffering is handle speed mismatch, slow printer versus fast CPU. It matches different data sizes and for example network packets versus disk sectors, and it provides you copy semantics applications can resume after writing to the buffer. So We have different types of buffers like single buffer, double buffering, circular buffering. In case of single buffer, one buffer between device and input output operating system is used. In double buffering, two buffers allow overlap. One fills while other empties. And in case of circular buffer, multiple buffers in rotation useful for streaming of data. Like you see the live telecast or live streaming of some football match or something. So circular buffers are used basically, which allows multiple buffers in rotation. So next we discuss about the spooling. Spooling is simultaneous peripheral operations online. So it uses a buffer, usually a disk area, to hold output for a device that is incapable of operating system at CPU speed. For example, using a disk buffer, it uses a disk buffer to queue jobs for the slow devices. For example, like printing jobs, which are stored on the disk, so printer fetches them at its own speed. So the key advantage is applications finishes quickly and user don't need to wait for the printing to complete. So the spooling is another concept of disk buffering. Then let's have an introduction about the RAID. RAID is redundant array of independent on or inexpensive disk. So RAID is a concept in which we use multiple disk drives to provide increased reliability via redundancy and increased performance via parallelism, because we are having multiple disks, so performance may increase by the parallelism. We are having different types of RAID levels. RAID 0, it is also called, it is based on the concept of striping. So in case of we use the block level striping, so data is split into blocks and spread across multiple disks. So benefit is high performance because you can, since because same data is copied on multiple disks, so you can perform parallel read and write operations. But the drawback is the failure of any one disk results in total data loss. Use case are high performance, where we require the high performance and the data is not critical. Like you can say like some video editing softwares or scratch disk like that. So in RAID 0, the data is the disk drives are there, multiple disk drives are there, and we have multiple blocks which are spread across the multiple disks. So A1, A2, A3, A4 and so on. Then we have RAID 1. RAID 1 is the mirroring. It is based on the concept of mirroring. It provides you complete redundancy. So every disk has a duplicate mirror disk. Advantage, high reliability, because read performance can be improved because you can read from either disk. Disadvantage is it is costly, 100%, because you are performing the same operation twice to perform in the original disk as well as in its duplicate mirror. It is critical for storage because it requires a lot of storage. If you see in RAID level 1, if you can see A1, A1, A3, A3, A5, A5, A7, A7, the blocks are duplicated. So it increase your efficiency, reading efficiency. You can read data from anywhere, but whenever you are updating, you need to update at the both place. It gives you the some safety, like if data is a disk data is lost, you can recover from the other one. Then RAID levels 4 and 5. 4 is a block level striping with dedicated parity bit. So we use a block level striping with a dedicated parity bit here, in which one disk holds parity information like XOR of data blocks for redundancy, and so it can survive one disk failure. But parity disk here becomes a write bottleneck. It creates a single disk bottleneck. On the other hand, RAID 5, which is block level striping with distributed parity. So it gives you a balance of speed plus redundancy. Parity blocks here are distributed across all the disk. So it eliminates the parity disk bottlenecks like RAID 4, and it is a very popular and common implementation. Like you can see here, RAID 4 and RAID 5. In RAID 4, one disk contains all the parity information, whereas in RAID 5, parity information is distributed across all the disks. Like disk 0 has the parity information for disk D disk, disk 1 has parity information for C disk 2 has parity information for B disk, and disk 3 has parity information for A disk. Then another RAID labels consist of RAID 6 and 1 and 0. So RAID 6, also known as a RAID 10, basically RAID 1 plus 0 is also called as RAID 10. So RAID 6 is similar to RAID 5 but uses two distributed parity schemes instead of one. So if it can survive the failure of any of the two disks, it uses the dual parity. And in case of RAID 10, we use a stripe of mirrors. So striping is over the mirrors. So it is a best mix of reliability and performance. Disk in this one, disks are mirrored in pairs like RAID 1. Then the mirrors are striped together like RAID 0. So it have the features of both RAID 1 and RAID 0. So it provides both high performance and high reliability. Like you see here, disk 1, RAID 0. So all the all the disks are separated. Under RAID 0, we have RAID 1. So A1, A1, A3, A3, A5, A5, A7, A7, we are having the mirroring. And in RAID 1 other side, A2, A2, A4, A4, A6, A6, A8, A8. So we are having the features of both RAID 0 and RAID 1. So if we provide the summary table, RAID 0 is based on the striping, so there is no redundancy. The performance is very high and overhead is 0%. RAID label 1 is mirroring. It uses the mirroring. Redundancy is there on one disk. It can perform hide, um, read and write operations, 100% overhead. RAID label 5 is based on striping plus distributed parity. RAID 6 is based on dual distributed parity. And RAID 10 is based on mirroring plus striping. Now, then the concept of stable storage comes. Stable storage is basically a conceptual model for absolutely critical data, like for financial transactions. So it guarantees that a write is fully completed and survives failure, or the data remains unchanged if write fails. If you're performing the write operation, so it ensures that either the operation completed successfully or the data has not been changed at all. Your data cannot be in the inconsistent state. It is achieved by replicated data across multiple independent storage volumes. So, which data structure is used by our kernel or the processor for the input output? Operating system maintains here objects for file for each open file, one object of type device for each hardware unit, and one object of type driver for each loaded driver. So these structures interconnect to the route of input output to route the input output requests correctly. As you can see here, the file description we use here, system wide open file table is there, and then we have a network information table and active inode table. So to improve the performance of input output operation, we can have multiple techniques like either reduce the number of context switches, minimize data copying, that is you shouldn't have the zero copy, use DMA, that is data memory access for large data transfers, and use interrupts. Use interrupts except at very high speed where polling can be faster, and balance the CPU, memory, bus, and device performance to avoid the bottlenecks. So, in summary, we can say that input output management is a core operating system function for abstraction and efficiency. Hardware mechanisms includes are polling, interrupts, and DME, direct memory access. Software layer consists of device drivers and APIs. Disk management is performed by different scheduling algorithms to optimize the performance, like we use the FCFS, SSTF, shortest seek time first, scan, circular look. Then advanced techniques we use for storing the temporary data, like we use buffering, spooling. Then we use the RAID to improve the throughput and reliability. And ultimately, efficient input-output management bridges the gap between fast CPUs and slower devices. So thank you so much. Let's see you in the week 5. And if you have any questions, just let me know. Thank you so much.